So Medtronic has been very interested in this because in the census that they had, all very good census, very good outcomes, they saw a really, really wide range of the power in the signal and also the number of subjects for whom there was a beta band. And this has been something that has been difficult for the census that didn't see it because they say their patients are doing well. So Medtronic is actually putting all the imaging and all the electrophysiological data together precisely to see if they can actually help the field in general with a more standardized way, if there is one, of where to push the lead. But it's very difficult because, people don't want to be told that they're not doing something right.
Hi, I'm interested in the crossover between what you're seeing in the Parkinson's DBS and the dystonia DBS for obvious reasons.
Yes. Thank you for that question. We actually did publish a study recording resting states in people with dystonia, actually with secondary dystonia, generalized dystonia, and showed in fact that there was a beta band in all but one person who didn't respond, who had a childhood encephalitis. So the word, though, in the literature is that in dystonia the rhythm is of a lower frequency. We're not so sure about that. We did actually see a beta in those people as well.
Well, maybe it's... Thank you very much.
For more, please visit us at stanford.edu. University. Thank you very much for the invitation to present here today. It looks like a great lineup. I agree. I'm very honored to be one of the speakers, and thank you for not saying all the other things that probably you could have said, although those were embarrassing enough. Actually, riding my bike every day even in rain and snow is just a statement about the traffic in Boston, actually. It's much worse to drive or even to take the T. But anyway, I'm going to not talk about the two topics I put in the title. In the title, I didn't pay enough attention to the timing, the amount of time I had for this talk, and I thought I could talk about development, which is really the topic that I care about the most, as well as nanobodies, new technology that we've developed, and I realized with 35 minutes I could only cover one of those, so I decided to cover nanobody technology because I hoped that some of you would find that useful, perhaps a broader interest, so I will start with that. So I'll tell you what nanobodies are in a moment if you don't actually know, but I'd just like to acknowledge Jonathan Tang. So Jonathan was a graduate student in the lab, and then he stayed on for a year as a postdoc. And really, all of the ideas, all these great ideas that I think are behind what I'm about to tell you about, and the majority of the work were done by Jonathan. So this picture here is a structure of GFT. This is sort of the star of the show for the first part of the talk. So we use nanobodies in a variety of ways, and I'm going to tell you three stories. The first two use nanobodies directed against GFT. The first story I'll tell you is about using GFT and nanobodies to drive transcription inside cells. The second one is to use the same GFT nanobodies to drive pre-recombination, and the last is an attempt to expand the use of nanobodies to any intracellular cell-type-specific protein to drive many different types of activities. So first, the motivation for these studies is probably the same motivation that many of you have. If we want to manipulate cells in a complex tissue, we like to have genetic access to specific cell types. And so we work in the retina, and this line up here is the bipolar cells instead of interneurons that we find in the retina. And we would like to understand how you can generate the diversity of cell types in the retina, or more generally in any complex tissue. And when Jonathan joined the lab, he wanted to study how these different types of bipolar cells get generated and how do they distinguish themselves. But we couldn't find lines of mice. We like to manipulate specific cell types using lines of mice in which pre or flip supercombinations are expressed in specific cell types. And when Jonathan started to look for those kind of lines of mice, he could not find them. But what he could find were lines of mice where GFT was expressed in subtypes of neurons, including in this particular example, two types of bipolars. So Jonathan and I couldn't bemoan the fact that there weren't recombinase lines for our studies, and we kept coming across these beautiful GFT lines. Here's actually a picture of that. Most of these GFT lines use cis-regulatory regions to drive expression of GFT. And in fact, there's a very large collection of those that are called the GenSat project, created by Matt Hines and his collaborators at Rockefeller, and you can just see some beautiful images of GFT-positive cells and subsets of neurons throughout the nervous system. Now, most of these are actually not cell-type specific. They light up a specific subset, more than one type usually, but they're quite useful for many applications that people have found. And again, they're created by these cis-regulatory regions. In the GenSat case, these are back transgenics. And we estimate from the GenSat as well as other people, there's quite a large collection, about 1,500 of such lines. So in looking at this, we realized this was an incredible resource in terms of giving us some type of access to specific